One of the hardest puzzles in both mathematics and physics is to solve the Navier-Stokes equations. These equations describe the behavior of fluid. They are not only essential for realistic fluid simulations in games and movies, but also play a crucial role in predicting turbulence in air, cyclones, and even the weather patterns. Solving a partial differential equation or PDE like this one means finding a function that predicts how the system evolves over time based on the initial conditions. Take this snapshot of a fluid. Now imagine I draw a set of vectors representing the velocities of fluid at different locations. If we use this velocity field as an initial condition in a simulation, the system will evolve naturally, showing how the flow changes over time in response to its surroundings. In fact, any future velocity field can itself serve as a new initial condition, allowing us to keep predicting the fluid's behavior further forward in time. And that's precisely what we want from an ideal solution: the ability to reliably predict the future velocity field of a fluid. Normally, the PDs are notoriously difficult to solve, but this one right here is quite challenging. So much so that even after 2 centuries of its formation, it still remains unsolved. And what makes this PDE much more interesting is that the Clay Mathematics Institute, or CMI, have established $1 million prize for anyone who proves any of the two possibilities. Either a valid and well-defined solution always exists, or the solution eventually becomes unbounded. That is, it blows up to infinity at some point in time. Now the challenge isn't about solving the equation. Even proving that whether a correct solution exists or blows up to infinity would be enough to win the $1 million prize. But why are the Navier-Stokes equations so hard and difficult to solve? Why does this happen? In this video, you and I are going to explore one of the 3 strategies proposed by Terence Tao as a possible path to tackle such a problem. And it's okay if this equation looks unfamiliar to you. We are gonna go over what each symbol means together. Some of these terms are quite easy to interpret, while others, they take a little bit more effort to build the right intuition. Let's make sure that we are on the same page. The Navier-Stokes model consists of these 3 equations, and we want to prove the existence of the solution to the first one. We have become quite familiar with the last one here, which describes the initial condition, and any valid solution, if it exists, shall satisfy this equation as well. The second equation describes the nature of the fluid. The inverted triangle signifies a special derivative, and its dot product with the velocity field gives us the divergence of a velocity field. Now, if any field is divergent like this one, it seems like the flow magically appears out of nowhere and then disappears into a void. In reality, we hardly see such type of phenomenon, especially in fluids like water. But by setting the divergence equals to 0, we are essentially demanding that the fluid's density remains constant everywhere and at all times. This is one of the 4 assumptions that we are going to adopt in our analysis. These curly D's that you see here, they represent how the velocity u changes in response to the change in position along x, y, and z direction. But before we move on, a quick note to clarify the difference between the x I used at 2 different places. This x in the partial derivative refers to the position along horizontal axis, and this kind of a bold x right here in this expression refers to a position vector. That the Navier-Stokes equation is valid for any d dimension. Now, the assumptions that we are going to take in our analysis, they keep our focus on the mathematical structure of the equation rather than us concerning about the physical aspects of the fluid model. Take viscosity for instance. Physically, it represents the resistance to flow. Think of this like a friction between the layers of the fluid. A high viscous fluid like honey moves much more slowly than a less viscous fluid like water. In our analysis, we treat it as a constant scalar parameter that strengthens or weakens the diffusion term. Also, the fluid should be Newtonian, which means that the viscosity shouldn't change under stress. If this were a real fluid, then it would contain billions of particles. You see, even only a teaspoon of water contains approximately a quintillion particles. If we zoom in on anywhere, we'll find billions of particles roaming around in space. But trying to track the motion of each particle isn't just impractical, it's outright impossible, even with modern supercomputers. So instead of treating the fluid as a discrete collection of particles, we model the fluid as a continuous medium. With this perspective, we don't worry about the path of each particle. We study the collective behavior of all of them together. And that's exactly what Navier-Stokes equations capture, a mathematical model of fluids as a whole. Finally, for our last assumption, we consider the fluid to be isothermal, meaning its temperature remains constant throughout the fluid. At first glance, this equation might look intimidating, but notice that if I multiply the equation throughout with the density, then this expression resembles Newton's second law of motion, F equals ma. On the right, we have the forces, and the left side expresses how the fluid responds under these forces. Every term influences the fluid's behavior in a different way, but these two terms are the most important ones. So before we go further inspecting these terms explicitly, let's simplify this expression a little bit. Since density is constant, we can set its value to 1 for simplicity. Okay, I know that viscosity is also a constant, but because it scales the diffusion term, it becomes an important factor. And we will see soon that this will determine whether the fluid remains stable or not. But external forces, Fe, is not that important in our analysis. This is due to the fact that if there is a blow up about to happen, it would be due to the advection term, not due to Fe, the external forces. Well, unless the force is funny enough to destroy the fluid and make the solution approach infinity. Moreover, if someone finds the correct solution, then Fe can be reintroduced through perturbation or energy methods. But let's not go there. Let's start with the simplest case, the 1D Navier-Stokes equation. Let's assume that our fluid flows in a straight line along the positive x direction. Now, if we stop the fluid at any instant and plot the velocity of the fluid at different positions, we get a graph of the velocity as a function of position. Here, the x-axis represents the position of a fluid particle and the y-axis shows its speed. These curly Ds represent the change in one quantity in response to another one. For instance, if I zoom in on the graph and draw a horizontal line showing a change in x position, I can trace how much the velocity changes in the vertical direction. We can approximate the change in u with respect to the change in x by taking their ratio. And this approximation becomes better and better as delta x approaches 0. This is called the differentiation of u with respect to x. Since velocity depends on both position and time, we use the curly d instead of normal d, which represents the partial derivative. The idea is that we are partially differentiating u with respect to x, keeping the other quantities like t constant. The similar thing goes on with t, which tells us how the velocity changes with respect to time. Now, we have got quite an idea about these two terms, but the diffusion term here needs a little bit more intuition. To understand this in more detail, let's focus on these three particles, P1, P2, and P3. For simplicity, let's take delta x equals 1. The diffusion term calculates the difference between the velocity of a particle and the average of velocities of its neighbors. The diffusion term is formulated as u1 plus u3 by 2 minus u2. And after a little algebra, this expression transforms to the differences between u3 minus u2 and u2 minus u1. Let's call them as delta u32 and delta u21 respectively. But you see, this is again the difference of two quantities. If I simplify it further, it would be delta delta u31. And this is analogous to the double differentiation of u with respect to x. Remember, we are dealing in 1D. Now, for higher dimensions, other spatial coordinates join as well. And this expression is called the Laplacian, represented by the inverted triangle squared. Okay, to see how u2 changes with time, we would take the operation of acceleration and diffusion term together. If the average of u1 and u3 is greater than u2, then u2 increases. But if the average is less than u2, u2 decreases. And this happens with every particle in the fluid. In essence, the diffusion term smooths out the peaks and valleys in the curve. The hills come down and the valleys go up. It kind of brings stability to the fluid, and the viscosity term just scales up this effect. The diffusion is a good boy. But if we do the similar analysis with the advection term, then the change in U2 depends on itself multiplied by U2 minus U1. Now, if U2 is positive, then U2 will try to follow its previous neighbor, U1. The rise and fall of U2 depends on whether U1 is larger or smaller than U2. And this can have a drastic impact on the velocity curve. Picture this velocity hill in isolation and analyze what happens just at the next instant of time. Particles' velocity on the left side of the peak slows down, while on the right side, particles' velocity speed up. As a result of this, the slope steepens, creating sharp transitions. The velocity curve remains no longer smooth, and this sudden change will result in the instability of the fluid, which can even lead to the shock waves, like the ones produced by the hypersonic jet. It's actually the non-linearity in the advection term that makes it a bad boy. So, we have a duel. Diffusion fights to stabilize the flow, while the advection pushes it towards instability. Which one wins depends on which term dominates. If the diffusion is stronger, then the fluid remains smooth. If advection dominates, then fluid will eventually become unstable. Now, our goal is to find a global quantity that can restrain this nonlinear advection, something that prevents this quantity from going haywire. But the question is, where do we begin our hunt for such a quantity? One of the remarkable properties about the Navier-Stokes equations is that they are scale invariant. In order to find a global quantity, we begin by scaling the equation. Suppose we scale the spatial coordinate x as x over lambda, where lambda is some positive scalar quantity. Now, by adjusting lambda, we can analyze the solution across different scales, much like using a magnifying glass to observe the space. And if lambda lies between 0 and 1, the scaled version would provide a wider scale perspective, a zoomed out view of the grid. But what we are interested in are the values of lambda greater than 1, where we find the finer details of the grid. So by increasing lambda, we can zoom into the blue grid and inspect the finer details, the local structures of our fluid. Think about this for a moment. If something fishy occurs, a blow up for instance, then it must happen at a local level or at some specific point. The blow wouldn't happen across the entire domain at once. That means by zooming in with larger lambda, we should still see the anomaly manifest, only compressed in space and slowed down in time. Since we have rescaled x, the spatial coordinate, all other quantities like advection, diffusion, and time derivative, they rescale as well. Let's define the scaling of time, velocity, and pressure as follows. And with alpha, beta, and gamma, take any real values. Now, with this formulated scale velocity u lambda, we can find out how the acceleration term changes. Now, as lambda raised to the power beta is constant, it can be taken out from the parenthesis. Now, when u is differentiated with respect to time, the coefficient of t, which is lambda raised to the power alpha, will come out. And this is a chain rule of calculus. And using the same rule, we can see the spatial derivative transforms as inversely proportional to lambda. And with this transformation, we simply can derive how the other quantities are transformed. You see, viscosity and density are constants, so they don't change on scaling. Now notice that, for the equation to remain scale invariant, each term must scale by the same power of lambda. So by equating these powers, we preserve the same mathematical structure under magnification, or under scaling. And this gives us the values of beta, alpha, and gamma. With this transformation, we can look at a zoomed in grid, but with a slower velocity profile, and at a much slower rate. Think of u lambda as a red grid, a slowed down version of the blue grid solution u. You see, if the nonlinear advection term blows up the solution, then the instability must appear at some finite scale, and we will be able to catch it. Suppose we want to know which one of these vectors is greater. Well, in this case, we use the Euclidean norm to measure the length of each vector and then do the comparison. Now, to compare our global quantity against the advection term, we need a way to measure the size of a function. But in case of functions, what does it mean for any function to be greater than the other? For the functions, we use the LP norm, which is defined as the integration of the pth power of the function's norm over the entire space. Let's call it u tilde p comma t. Just a quick note here. The x in the dx is the usual position vector in any d dimension, and this dx represents a tiny elemental volume in the d-dimensional space, and the omega refers to the whole spatial domain. Because the LP norm analyzes the equation in the entire domain at a given time t, there is no explicit x in the notation, and no dependence of space on u tilde. Instead, we got another parameter p, a real number greater than or equal to 1. Now, to keep the units consistent with velocity, the integral is raised to the power 1 by p. LP has different meanings, has different physical aspects for different values of p. Take p equals 1 for instance. Although this doesn't represent anything physically as much, but gives us a sense of how the fluid spreads throughout the space as a whole. But p equals to 2 is an interesting case. This quantity inside the parenthesis is the kinetic energy of the fluid. And going by the conservation of energy, we know that the kinetic energy cannot blow up to infinity. In fact, some of the kinetic energy actually transforms into the heat due to the viscosity. And in the absence of external forces, this is the expression of kinetic energy which depicts that the energy actually decreases with time. And this expression can be derived by taking the inner product of Navier-Stokes equation with the velocity u. So in 3 dimensions, it is safe to say that u tilde 2, t remains bounded at all times. Now, with these two mathematical tools, we can eliminate the dependence on the explicit vector quantity x and replace it with two scalar ones, lambda and p. After substituting the expression of u lambda back into the integral, we can track how the LP norm changes under scaling. We know that in d dimensions, each coordinate transforms as x by lambda. Let's focus on this power factor, and plotting this relationship shows us how the function size behaves when we zoom in further and further. Now, based on the power factor, there are three possibilities. The first one is when p is less than d. In this case, the ratio blows up as lambda increases. Such quantities are called supercritical. For example, in 2D, p equals 1 term is supercritical, and in 3D, p equals 1 and 2. Both are supercritical. But such quantities have serious problem. Even though we have proved that the kinetic energy in 3D remains finite at all times, the energy can still concentrate and blows up as lambda increases. So if a global quantity, which we are trying to constrain the nonlinear advection term, lies in the supercritical category, we cannot use it to control the nonlinear advection term. Supercritical quantities are of no use at all. Now, these are the quantities that fades out as lambda increases. Such quantities are subcritical. So, if our global quantity lies in this category, it may or may not help us in proving the existence of our solution. But this case is the most interesting one because these quantities, the critical ones, actually give us some hope. They remain unchanged under scaling, no lambda dependence at all. And such invariance makes them stronger candidates for controlling the advection nonlinearity, and they may hold the key to proving the existence of smooth solutions. Consider the kinetic energy in 2D. As it is a critical quantity, it also remains invariant under scaling. There is no dependence on lambda. In other words, the 2D kinetic energy doesn't blow up at smaller scales. It remains bounded as lambda increases. In fact, using this concept, Olga Ledzinskaya proved that there exists a smooth solution for Navier-Stokes equations, but in 2D. Although she didn't use the exact terms as critical or subcritical in her proof, as these terms came much later, but the underlying principle is same. Well, this opens a window for us, a small but a hopeful one. So, I leave you with this. If we look at u tilde 3, t in 3 dimensions, which is also a critical quantity, can it play the same role? Can it control the nonlinear advection term? Can it confine it somehow? And if not, might there exist some other critical or subcritical quantity that could? Of course, what we discussed here is only one of the several strategies mathematicians have pursued, especially in recent decades. Countless attempts have been made to prove or disprove the existence of smooth solutions in 3D, but the Navier-Stokes equations are still unsolvable. These equations remain a mystery to physicists and mathematicians. So while we can freely forecast cyclones, turbulence in the air, and predict weather, or even simulate fluids with astonishing realism in Blender or visualize them in Manim like this one, the underlying mathematics of these equations remains elusive. So it seems quite tempting to call the Navier-Stokes equations a perfect model for the fluids. But are they really?